12.2, chords and arcs. A chord is a segment whose endpoints are on a circle. So you can see here in your diagram, you have chord PQ. So you would write the name of that as segment PQ, but it would be defined as a chord because it has both endpoints on the circle. When we deal with chords inside of circles, we also have related arcs to those chords. So in this case, chord or segment PQ and arc PQ are what are called related to each other. So when we say it's related arc, we have to know what we are referring to. Now, within a circle or in congruent circles, it could be either case. If we have congruent central angles, they have congruent chords. Once you have congruent chords, you can say you have congruent arcs. And then congruent arcs come all the way back around to having congruent central angles. So there's three things basically that you can say are congruent in the same circle or in congruent circles. It just depends on what you're given really as to what you'd be able to tell after that. Number 3 here, we're showing two congruent circles, circle O and circle P, and we're given that arcs BC and DF are congruent to each other. So the conclusions that we can come up with from here come back up here to this theorem that we just talked about. Once we know we have congruent arcs, we can say we have congruent central angles. So angle O is congruent to angle P. And then once we have congruent arcs and then congruent angles, we also have congruent chords. So the chords in this case would be segments BC and DF that would be congruent. Now, if we use the same picture in number 3 for number 4, but we're changing the information that we're given, we're now told that the chords are congruent instead of the arcs being congruent like they were up here. This changes just one of our answers. If we have congruent chords, we still know that we would have congruent central angles. So angle O is still congruent to angle P. But now the second answer is what's different. We would now be able to say that the related arcs, so arc BF and arc DF, are congruent to each other. Another theorem that deals with chords within circles is, again, within a circle or incongruent circle, chords that are equidistant from the center are congruent. Now, this term equidistant, you have to remember, means that they are the same distance away from something. And hopefully you also recall, and maybe it would be a good idea to add this in your notes as well, when you're measuring from a point to a line, or in this case from the center of the circle to a chord, you have to measure at a perpendicular relationship. Once we have congruent chords, we would be able to say they're equidistant from the center. So those two things are really just converses of each other, depending on the information that you're given. Under number 6 here, we have 2 examples. Neither one of these really requires any work. It's just you have to understand what you're looking at, be able to identify the information you're given, and then see what conclusion you can make from that. So in part A, what we need to see in this picture is that we have chords that are congruent, because this chord on the right is 36 and the chord on the left is 18 and 18. Those two halves make a full 36 for the whole length. And we can say that they're perpendicular to the center. So the lines coming from the center point of the circle out to each chord are perpendicular to those chords. Noticing those 2 pieces of information allow us to make the conclusion that X would have to be 16. Because we know the chords are congruent, and when we start measuring from the center out perpendicular to those chords, since the chords are congruent, those segments from the center to the chords have to be congruent as well. In part B, what we need to see in this is that the chords are equidistant from the center. So there's 2 parts that go into that. First of all, the segments that are coming from the center and intersecting those chords, are perpendicular to those chords. So we have those 2 right angles. So that's the first part of being equidistant. The second part is that those segments are also congruent to each other. So they're both length 9 as well as being perpendicular. Based on that, we could conclude that these 2 chords are congruent to each other, which if chord PR has a length of 25, that means that variable A would have to be a value of 25 as well. Even more theorems that deal with these chords. Be totally honest with you, you just have to flat out study these. There's no other way around it. In a circle, a diameter that's perpendicular to a chord bisects that chord and its arc, actually both arcs, its minor arc and its major arc. In a circle, a diameter that bisects a chord, as long as that other chord is not a diameter, is always perpendicular to the chord. And then in a circle, the perpendicular bisector of a chord contains the center of the circle. So really, these three theorems are all pretty closely related to each other. It's just based on what information you're given and what information you're able to come up with or what conclusion you're able to make using that information. So number 10, parts A and B will use some of those theorems that we just looked at in order to find the missing lengths of these within these circles. So in 10A, what we have to look at is that we have part of a diameter, this KN segment here. We know it's part of a diameter because it comes from the center point and it's perpendicular to this chord LM. Now, because it's perpendicular to that chord and from the center point, we know that it's bisecting that chord. That's using theorem 12.6 from above. Now, once we have this, we can just focus on this right triangle, triangle KLN, and use Pythagorean theorem to figure out that missing radius. So the radius would be the hypotenuse of that right triangle. So we would set up Pythagorean theorem like this. Then when we simplify, we would find that the radius is approximately 7.616 centimeters. Now in part B, there's some information that's supposed to be given to you, but it's missing, so I apologize for that. But now we're given that segment CB is perpendicular to segment AC. So we can go ahead and show that those two are perpendicular to each other. That will allow us to work a little bit more with the problem here. The way that that's given to us is that we have a segment or part of a diameter because it's coming from the center and it's bisecting a chord. So a diameter that bisects a chord is perpendicular to the chord is theorem 12.7. Now again, we have that right triangle, so we could set up Pythagorean theorem. We're finding one of the legs this time instead of the hypotenuse. And as we work our way through that, we would have y being approximately 10.198 units. In number 11, we have another circle. We have, notice some information. The radius of this circle is 6.8. The distance from the center to the chord is 4. Now, if I'm saying distance from the center to the chord, that has to be perpendicular, because that's the only way we measure distance from a point to a segment or a line or a ray. If we want to find the length of this chord, what we first need to realize is that since we have part of a diameter from the center of the circle that is perpendicular to our chord, that chord is being bisected. So I've called half of that chord y. So instead of finding the length of that actual chord first, I first need to find the length of y, the missing leg of that right triangle that I see in the circle. So as we work through Pythagorean theorem, we figure out that y is the square root of 30.24. Notice I haven't rounded this yet. I don't want to have to round until the very end so that my answer is as exact as possible. Now, if I'm trying to figure out x, which is the length of that chord, if y is square root of 30.24 and y is half of x, I could just double the y value, which is square root of 30.24, and find that x is approximately 10.998 units. Part B tells us to find the distance from the midpoint of the chord. Remember, this is being bisected, so this midpoint is the intersection of this segment that's 4 units long and this chord to the midpoint of its minor arc. So here's the minor arc that's related to this chord. The midpoint would be directly, if you continued that line straight to the edge of the circle, the distance from the midpoint of the chord to the midpoint of its minor arc is what I have labeled here as Z. What's important to notice here is that we have a full radius. If we were to combine these two segments, the segment of 4 and this segment Z here, make a full radius, and we already know the length of the radius of the circle is 6.8. So we can very quickly find Z by just doing a little subtraction, and Z would be 2.8 units. For number 12, I'd like you to read the information that you're given and sketch yourself a picture. Yes, it would be nice if you use a compass and a straight edge so your circle is actually circular and your lines were actually straight. If you don't have those with you, not the end of the world to sketch it freehand. But see if you can sketch this picture based on the information that you're given. Here's what that picture would look like based on our information. I have my circle with the center point labeled as O. I have my chord, P and Q. Those could be flip-flopped, it doesn't matter. Your chord could be somewhere else on the circle as well. It does not make any difference. The distance from the center, O, to chord PQ is 15 inches. So that means I have to label that part of that diameter from the center to the chord as 15 inches. And I also need to make sure I have my right angle labeled, because that's, again, the only way we measure distance from a center or a point to a chord, line, or ray. And then it also tells me the length of that chord PQ is 16, so I have that labeled as well. Now your job is to find the radius of circle O. Finding the radius of circle O, first thing you'd want to maybe do is draw in a radius. So connect from the center of the circle out to, I would say, either endpoint of the chord PQ. Now, if we're trying to figure out what this radius is, we need to realize that chord PQ is bisected by this portion of a diameter from the center of the circle to that chord. So we would have 8 for the remaining leg of the right triangle. So when we do Pythagorean theorem, trying to find the hypotenuse, we would just need r squared equals 15 squared plus 8 squared, and that results in a length of the radius being 17 inches.